Our speaker tonight, Michael Turner, he's a theoretical cosmologist, and he coined the term dark energy way back in 1998. We've been living with it ever since. What is dark energy? Well, we'll maybe know a little more about it tonight. Um, he is from the University of Chicago. He was formerly the assistant director for mathematical and physical sciences for the U.S. National Science Foundation from 2003 to 2006. In his book, The Early Universe, was written with fellow Chicago cosmologist Rocky Kolb, and that was published back in 1990. It's the standard text on the subject. Michael received his BS in physics from the California Institute of Technology in '71, picked up a Ph.D. in physics from Stanford in 1978, and he helped establish the interdisciplinary field that combines together cosmology and elementary particle physics to understand the origin and evolution of the universe. And his research focuses on the earliest moments of creation. And Michael's made contributions to inflationary cosmology, particle dark matter, and structure formation, the theory of the Big Bang nucleosynthesis, and the nature of dark energy. Please welcome for the first time to the Westport Astronomical Society, Michael S. Turner.
Thank you. Can you hear me?
Yes.
Okay, great. Let me share my desktop here. I've been really enjoying myself letting you guys do all the work. Everybody can see that?
Yes.
Everybody can hear me?
Also, yes.
Yep.
Okay, terrific. Boy, I really enjoyed that, but this is really going to be a different experience now. We're going to elevate ourselves to the universe. Not going to talk much about stars or planets or nebulae. But I want to tell you what we know for sure, what we're in the process of establishing. And then I understand you guys really like wild speculation. So I've thrown a little bit of that in there. And I thought this would be a good starting point. Everybody knows the universe is big, and I'll get back to that in a second to get us going. But it's often beyond the reach of our eyes or even our instruments and our minds. And the struggle to understand the universe, it's really pushed us to the limits in both areas. And this last century has really been quite remarkable and I'll come back to that a little bit after I tell you about what we do know. It's been a remarkable century of discovery that's been driven both by big ideas and powerful instruments. And probably you all recognize, actually, this is one of your star parties that I once attended. I see Shannon there. I see Dan. Of course, this is Galileo. This is 400 years ago. And now we have these enormous...
Bob was there for that one.
Those were the old jackets.
That's right. Where's the jacket? Yeah, they were quite a bit nicer then.
We don't have fringes anymore.
We've now got these big reflecting telescopes on top of mountains. This one here, 4 8.5-meter telescopes in Chile, the European Southern Observatory. Oops, I accidentally went on to the next slide here. A couple of Magellan telescopes, and probably you recognize the Keck's, and 100 billion factor of improvement in sensitivity. And then, of course, we now have telescopes in space. Everybody recognizes the Hubble, the Chandra. Let's see. I have to be careful with my mouse here. And this is the Fermi telescope, so that's gamma rays, and there's the Spitzer telescopes. But equally important are the ideas. And some of the big ideas, here's Einstein, and his general relativity is the framework for understanding the universe. This is Feynman's last blackboard. Feynman was one of my teachers at Caltech, and so I had to put that up there. And Feynman and Gell-Mann were responsible for quarks, and the universe began as quark soup. And then down here is Alan Guth, and this is a page from his notebook, and it's boxed. It says spectacular realization. This is December 7th, 1979. when he discovered this idea of inflation that we'll be talking about. So the big ideas. So I find myself, the older I get, talking about what science is, and particularly at this time when science is playing a particularly big role. I'm going to give you my 3-bucket theory of science because it really frames the talk here. So bucket number 1, what we know for sure, knowledge that's not going away. That means we have very strong evidence. So that's part 1 of the talk, what we know about the universe. Bucket 2, I've yet to come up with a good name. Maybe someone will come up with a better name here. I call it knocking at the door. So some ideas where there's some evidence, we're pushing for more evidence, but we wouldn't want to go out on a limb and say we know this for sure. And then bucket 3 is the best one, at least for theorists. Crazy ideas, wildly speculative, guesses, hunches, anything. It could come in from anywhere. And the way this process works is you start with bucket 3. And some of the ideas from bucket 3 make it to bucket 2. So those are the ones where you get a little bit of evidence and they're worth testing. And then you go from, some of them go from bucket 2 to bucket 1, where it's the stuff we know for sure. And cosmology, I really hate most of the cosmology textbooks because they mix all the buckets up. And I think that's a disservice to science, and it's a disservice to what we know about the universe. It's a disservice to science in the way that, oh, well, that's what they thought today, and they'll change their ideas tomorrow. Well, there's certain, in bucket 1, those ideas aren't changing. So part 1, what we know for sure about the universe. Okay, so this is not going to surprise anyone, but it's kind of a warm up. The universe is really big, really big. I'll show you the big numbers at the end. I bet you all recognize this picture. Anyone not recognize the Hubble Deep Field? And you can, about 1,500 galaxies in this image, a couple of stars. I'm not going to dare point at this. Here's one star. I think that's another star. That may be all the stars. And 1,500 galaxies. This is about a 30 millionth of the sky. It's a very tiny fraction of the sky. And if you combine those numbers, it's 200 billion galaxies define the observable universe. And I'll just pause here because probably you all know this, but I'll just pause and say it anyway, is the dark spaces between the galaxies are really dark. That's as far as we can see. It's, if we build a more powerful telescope, the James Webb, we're not going to see any farther. And so the reason that we can't see any farther is something that you all know. As you look out into space, you look back in time. And when you look far enough back, you look back to a time before there were galaxies. And so you can't see anything back there. So this is basically answers the big question, how far can you see on a clear night? And the Hubble answered that. Boy, I thought I was going to be so smart. Here's the Milky Way, and I just put this up. This is an infrared image of the Milky Way, 100 billion stars. So continuing with the big numbers. And I thought I was going to be so smart because I looked at Delphinius and noticed the globular clusters. And I thought, no, but I want a galaxy. And so there's NGC 7025. And what I like about this is an image from the Sloan Digital Sky Survey, a project that I was involved in. And maybe I'll have 1 second to talk about it later. The way the universe is organized, the basic building block of the universe is a galaxy, but the galaxies sometimes cluster together in what we call clusters of galaxies. Closest cluster is Virgo. It has a couple hundred galaxies that are shown in this image. It's about 50 million light years away. And we have been voted into Virgo. We are going to become a member of Virgo. We are at the moment falling in. We actually do not have a choice. So the gravity of Virgo is pulling us in, and in a few billion years, we'll be a member of the Virgo cluster. So this is soon to be our cluster. One of my favorite clusters is Coma. Coma's got a couple of thousand galaxies in it. It's about 300 million light years away. And how is the universe organized on the biggest scales? So this is from the 2D galaxy redshift survey. The Sloan has a similar picture, not quite as pretty, although I was involved with the Sloan. And I'm not sure if you're familiar with these wedge diagrams, but we're here, right there. And this is a small wedge of the universe. So this is angle across the sky, and this is distance away. So you get that distance by measuring the redshift. And each little dot is a galaxy. I think there are probably maybe 60,000 dots here. And what you see is that the galaxies are not uniformly distributed, at least on the smaller scales. You see voids. If we looked at this and rotated it in 3 dimensions, you'd see sheets and filaments. But on the largest scale, the universe is homogeneous. The structure repeats itself on the largest scales. And we'll come back to that. The reason that the universe fades out here is something that you guys know better than I do, is in astronomy, almost always the surveys are flux limited. And so in this survey and in the Sloan survey, as you go to farther distances, you can only see the brightest objects. And so you only see the brightest objects, and there's not that many brightest objects. Okay, the big numbers. 100 billion improvement in our ability to see the universe since Galileo. 100 billion stars per galaxy, a similar number of planets, 100 billion galaxies, each with a big black hole at the center, 1 million galaxy clusters, and the observable universe is about 30 billion light years across. And it is and we know the universe is about 13.7 plus or minus 0.1 billion years old. So the universe is really big. We actually, I was very careful to say the observable universe because we don't know how big the universe is. This is the part that we can see. We don't think the universe ends right where at our light horizon. Okay, then the next thing that we know for sure is that the universe had a beginning, and that in the beginning, the universe was a lot simpler. It was quark soup. And so this goes back to 1929 and Hubble's discovery of the expansion of the universe. So I put this slide up here. This is our galaxy, other galaxies. Hubble noticed that the galaxies were all moving away from us. They all had redshifts, and the ones that were farther away had larger redshifts. And I think you all know that this, if you took away the galaxy images, which I won't do, this looks like the signature of a Big Bang explosion. So if all the galaxies were in one place, say 13.7 billion years ago, and they went hurling out, I'm going to tell you to drop this metaphor in a second, but anyway, keep it for 1 second. The ones that went further are the ones that are moving faster. So that's the simple interpretation, that there's a Big Bang, but of course that interpretation says, oh, isn't that funny that we're at the center of the Big Bang? Yeah, how did that happen? Are we special? And this is where the first big idea comes into play. Einstein, in his theory of general relativity, space is flexible, space is dynamical, and the expansion of the universe is not matter hurling into empty space. It's the expansion of space itself with the matter being dragged along. So the universe is just getting scaled up. The galaxies are being pulled with it. And so the Big Bang was everywhere. And there's no argument because at the Big Bang, everyone was on top of everyone. And so everybody could say, I'm special. The redshifts, why are the light from distant galaxies have a longer wavelength? Well, it's not really a Doppler shift. It's the expansion of space. And that's a very cool thing. So the wavelengths of photons are stretched by the expansion. And when we measure the redshift of a distant galaxy and add 1 to it, what we get back, 1 plus the redshift, is the size of the universe today divided by the size of the universe then, how much the universe has expanded. At one time, let's see, I think this is a Sloan quasar. At one time, this was the highest redshift quasar. It had a redshift of 6.43, which means that the light is shifted by a factor of 7.43. So Lyman alpha, I guess if you guys know what H alpha is, you must know what Lyman alpha is. And so Lyman alpha, which should have a wavelength, let's see, let me put this in, 1216 angstroms in the ultraviolet. For this quasar, it's at 9,000. So it's been shifted from too blue to see to too red to see. And that tells us that the universe was 7.43 times smaller when the light from that galaxy was emitted. Okay, so that's the Big Bang, but it was a hot Big Bang. And that brings us to the microwave background. 1964, Penzias and Wilson discovered some mysterious microwaves coming from all directions, all times a day. And we now know that what they are is the universe is filled with microwaves characteristic of an object at temperature of 3 degrees above absolute zero. So the temperature, the average temperature of the universe today is 3 degrees above absolute zero, which is a pretty boring temperature, very, very low. But as the universe expands, it cools. So if we look at the temperature of the universe, as the universe expands, it's going down, so it's going to get even lower. But if we go in the opposite direction and ask, how hot was it in the past? It was really hot. To use a technical term, hotter than hell. And so the universe began from a hot Big Bang. And when you heat something up, you reduce it to its most basic constituents. And that we know from particle physics is quarks and the related particles. And so that means that the universe way back when at the beginning, when it was hotter than hell, was quark soup. So we can now trace the history of the universe from quark soup to us. And the part that we understand really well begins around 10 to the minus 5 seconds when the universe is hot quarks. And around that time, it becomes cool enough for the quarks to condense into neutrons and protons. A few seconds later, some of those neutrons and protons combine together to make the lightest nuclei in the periodic table: helium, deuterium, lithium. And these elements were made shortly after the Big Bang. We can calculate how much of them were made, and we can compare that with what we see, and that's an important test of the Big Bang theory. Then the universe is cooling, it's getting bigger, and around 400,000 years, it's cool enough for atoms to form. And once the atoms form, the universe becomes transparent to light, and the radiation in the universe, at that time, the universe was about as hot as the surface of the sun, a few thousand degrees. So all that radiation now just freely streams to us, but it's redshifted by the expansion of the universe by another factor of 1,000, and that's the microwave background. So we can trace the universe from quark soup I'll talk more about going from atoms to galaxies a little bit later. But we know that that's something that we know for sure. And an important test of this is the abundance of these light elements and the microwave background. Yeah, I'm gonna, maybe, I don't know if I have this slide later, but I'll talk about this. It's a blow up of the last frame here. This is when the universe goes from ionized matter, when it's very opaque to radiation. So a photon trying to get to us would constantly be bumping into electrons. The atoms form and then they stream right to us. And so this is called the surface of last scattering. Now you all know about the surface of last scattering, say for the sun. So when you look at the sun, the light came from the center of the sun, but it last scatters on the surface. Here it's a little bit different. It's the universe when it was about 400,000 years old, not 400,000 years ago, almost 13.7 billion years ago. The universe since then has grown in size by a factor of 1,000. But what we're seeing when we look at the microwave background is the universe before stars were formed, before galaxies were formed. And so there's an enormous amount of information in that. And I'll come back to that. I'll also talk about when most of the stars were born and so on and so forth. But the universe lit up around 1 billion years after the Big Bang. And here we are about 13.7 billion years. So far, I've talked about what we can see with light, but it turns out most of the universe is dark stuff. And I know about a month ago, Katie Fries told you about dark matter, and I'll also tell you about dark energy. So most of the matter in the universe is unseen dark matter. The universe is held together by the gravity of unseen dark matter. How do we know that? If you look at a galaxy, the stars, as you know, in a galaxy orbit the center of the galaxy. The gravity of the stars that we see in a galaxy is not sufficient to hold the galaxy together. You need dark matter. That was the work of Vera Rubin and others. And then earlier than that, Zwicky showed that the same is true in clusters of galaxies. And there's our friend Fritz Zwicky. There's a new biography of him that I have to recommend. It's absolutely fantastic. Brilliant. Yeah, that's what his colleagues said. He didn't play well with others. And in 1933, he discovered that galaxies and clusters were moving so fast that the gravity of all the stars and all the galaxies couldn't hold the clusters together. And so he coined the phrase dark matter. The paper's really interesting because it's not really about dark matter. It's about his theory of the redshift. And also he had a lot of crazy ideas. Many of them were correct. And so people didn't really pay attention to him. Vera Rubin really brought the problem closer to home, showing that in our own, not in our own Milky Way, but this in Andromeda, that was one of the first galaxies where the rotation curve was measured. This is the velocity of stars orbiting the center of Andromeda. And this is so easy to see what the problem is. Here's all the light. These stars out here are very far away from the center. How come they're moving so fast? That's because there must be a dark matter halo. This is 2013. Vera died a few years ago, but we honored her for her discovery. The American Physical Society did, and I was presented a plaque that's there at the Department of Terrestrial Magnetism in Washington, D.C. in her honor, and that's a picture of the two of us together. Yeah, so dark matter, I'm going to jump to the bottom here. Without the gravity of dark matter, we can't make the observed structure. There's no shortage of evidence for dark matter. We can't explain the universe without it. And probably Katie Fries did a really good job of telling you about dark matter. But dark matter is there. We just don't know what it is. The accelerated expansion. So on your mother's knee, you saw this, right? Your mother was telling you about the Big Bang. Here's the size of the universe. Here's the Big Bang. The universe is getting bigger. There are three possibilities. In a universe with lots of matter, in any universe, the expansion is slowing. In one with lots of matter, it eventually stops expanding, reaches a maximum size, and there's a big crunch. You remember that. And in a universe with not very much matter, eventually the universe gets big enough that the effect of gravity is not important anymore, and it no longer slows, and this becomes a straight line. And then there's the Goldilocks universe that slows and slows and slows. It's all slowing. That makes sense because gravity is attractive. Well, in 1998, as probably everyone knows by now, we were surprised because the universe is not slowing down, it's speeding up. What is going on here? So actually, this is a wonderful story. The evidence was not that great in 1998, but the evidence got stronger. We now know with certainty that the universe, the expansion is speeding up. Why is it speeding up? Well, it turns out that repulsive gravity is a feature of Einstein's theory. Deeply buried in his theory, very weird stuff, I'll tell you a little bit more about it, has repulsive gravity. What do I mean by repulsive gravity? I don't mean that, you know, the subject is repulsive to study or that it's difficult. I mean that instead of gravity attracting, it pushes things apart. And so I coined the phrase that we call that stuff dark energy. So let me tell you a little bit about it. Its defining feature is it's extremely elastic. Ordinary matter has positive pressure. If you look at the sun wants to expand. If you have a cold gas, it doesn't want to expand or contract. It has very little pressure. The dark energy is stuff that's elastic. Its pressure is negative. So instead of wanting to push out and get bigger, it wants to contract. And in fact, I won't go into the details here. I was told I was allowed to have two equations. So its pressure is really, really negative. And it's smoothly distributed. It's not particulate. So it's more like a medium. And you might say, okay, well, it would be very helpful to have an example so that we could better understand dark energy. Well, here's the example. The quantum energy of nothing. The quantum energy of nothing. So it turns out that nothing is not nothing. According to quantum mechanics, the vacuum is filled with particles living on borrowed time and borrowed energy. Actually, I remember a couple of elections ago, that was the economic plan of one of the candidates. I wish we'd go back to talking about things that boring. So these virtual particles that fill the vacuum, so you have an electron and a positron pop out of the vacuum, borrow some energy, and then disappear. The existence of these virtual particles has been measured. It changes the spectrum of hydrogen. So there's a shift of hydrogen lines called the Lamb shift, for which Willis Lamb, I think, got the 1955 Nobel Prize. Now, here's the part you're going to have to trust me on. So the vacuum, the quantum vacuum is filled with these virtual particles, and they have negative pressure. Now, I can spend an hour explaining it, but probably you don't want to hear that. You'll take my word for that. And so, in fact, the gravity of the quantum vacuum is repulsive. And how repulsive it is depends on how much nothing weighs. Are you with me on this part of the Zen talk? So how much does nothing weigh? Well, this is where theorists start getting really nervous because our estimate is about right. It's only off by 55 orders of magnitude. And the short version of it is that we think that the vacuum weighs, well, to be perfectly honest, our calculations give infinity. If we use some tricks from advanced mathematics, we can get it down to a factor of 10 to the 55 too big. What I mean is that the universe would be expanding 55 orders of magnitude faster than it is today if the vacuum weight is as little, the smallest number we could get. So this is quantum vacuum energy. Einstein would have called it the cosmological constant, is one possibility. The universe is accelerating. We don't know why. We think it's the repulsive gravity of dark energy. Okay, structure built by gravity. So here's a nice picture of the microwave background. This is the best map we have. This is taken by the Planck satellite. It's false color, and where it's red, the density of matter is higher by about a part in 10 to the 5. Where it's blue, the universe has a density that's lower than about a part in 10 to the 5. And so the universe was slightly lumpy, very slightly lumpy. Actually, what did I circle here? So, you know, I'm out here in California now, and product placement is a really big deal. And this is to show you how great Stephen Hawking was. He got his initials placed in the microwave background, SH. You see it? Product placement. You want Stephen Hawking's agent. This is a map of the universe, slightly lumpy. Gravity takes that lumpiness, and where there's more matter, the gravity is stronger, more matter is attracted in. You've probably seen some of these computer simulations. You take a universe that is very nearly smooth. The variations in the density are 0.001%. You let gravity run and on a computer, and you get the structure that we see today. So gravity in the universe is the master builder. And this is another test of our understanding of the universe. Is we take this degree of lumpiness, we take 13.7 billion years of gravity acting, and we get the structure that we see today. Oh, I know you guys love stars. I'm not a big star guy, and so this, our understanding of the universe and our instruments are so powerful that we can trace star formation from, this is redshift 10. So that's when the universe was 11 times smaller. Here we are today. This is a log scale for star formation. And star formation peaked at redshift of about 2 when the universe was about 3 billion years old. So we can track that. This really explains a lot. When I grew up, there were a lot of stars. There were the Rolling Stones, there were Janis Joplin, there were the Beatles. And nowadays there's very few. I mean, you got Lady Gaga and maybe a few others. That's because the rate of star formation has dropped so precipitously, almost a factor of 30 here. And of course, on the computer, when we simulate the expansion of the universe, we see that galaxies collide. Hubble is caught colliding galaxies. Oh, quasars. Somebody can ask me a question about quasars later. Let me talk about this remarkable century. If we go back 100 years, 1900, 8 planets. We didn't know what powered the sun. We thought it was just cooling off, and based upon how much heat it had, it should only have about 10. It should cool in about 10 million years. We knew of one galaxy. With the telescopes of the time, a few million stars were visible. We thought the universe was static. Well, this was exciting. The Yerkes telescope that my universities ran, the 40-inch Yerkes refracting telescope, was the biggest one in the world. It used photographic plates. Here we are today. We still have 8 planets, but we know that the solar system is only 4.6 billion years old. The sun is powered by nuclear fusion. We know of many other planets. So the number of planets actually stayed the same. A universe that began 13.7 billion years ago, 100 billion galaxies, so on. We still don't know how big the universe is, but it's a size greater than 10 billion light years. That's what we know for sure. Let's go on to knocking at the door. So I suspect you heard a lot about this from Katie Fries. Dark matter. I didn't tell you the most exciting thing about dark matter. The amount of dark matter is about 30% of the critical density. We know how much ordinary matter there is. We can measure it several different ways, and it's about 5% of the critical density. And so this is an accounting problem. I don't know if we have any accountants in this club, but 30% is bigger than 5%. So we're missing 25% in our book. Somebody, the total amount of matter is 30%. Atoms is only 5%. So most of the matter is not atoms. It must be a new form of matter. And we think it's particles left over from the Big Bang and from that quark soup phase. So we're in the part where we don't know this for sure. And here are our best hunches. In fact, this is a slide I made in 1990. So our best hunches have stayed pretty stable. One is a particle called the axion. It weighs a lot less than the electron, but there's a lot of them left over from the Big Bang if the axion exists. I'll come back to that. Another is called the neutralino. It's the lightest particle predicted by superstring theory. It weighs, maybe 100, maybe 1,000 times what a proton does. And then you've all heard of neutrinos. For a brief amount of time, we thought that the dark matter might be neutrinos. We know how many neutrinos are left over from the Big Bang. But neutrinos, we now know not precisely what their masses are, but we know the biggest their masses can be. And so they cannot contribute that 25%. I forgot to mention the axion and the neutralino are both hypothetical. Now, the good news is they were invented by particle physicists not to solve the dark matter problem, but for other good reasons. And when we asked how many would be left over from the Big Bang, the answer is about the right amount to account for the dark matter. Let me see what, okay. So this was our best idea. Axions and neutralinos, we showed that the neutrinos couldn't work. And Katie probably told you that there are different ways to test this dark matter idea. You could produce them at an accelerator. You could detect the ones in our halo of our galaxy that hold together our galaxy. And in fact, there are experiments in all of these directions, but so far they haven't come up with anything. Well, maybe tomorrow. They've just reached the sensitivity where they could see something. Or maybe we need a new idea. Oh, actually, this was a slide I made in 1980 before we pared down the list. This is a new list. So when theorists, when their best ideas don't work, they now make a map of all the new theories of dark matter. Katie may have shown you this. So the dark matter story is not done. We know dark matter is there. Our best hunch is a new form of elementary particle left over from the Big Bang. Okay, dark energy. Okay, what is it? Well, let me first tell you how important it is. And I want to answer a question that someone might have had about this diagram. So this diagram has all these droopy lines. So what's going on here? Well, what we've actually measured is that the expansion rate is speeding up. So that's the kind of line that bends upward. And the story that your mother told you on her knee was that the destiny of the universe was related to its shape. It turns out that's not true if you have dark energy. So we are actually the Goldilocks universe that's uncurved, but we're also speeding up because of the dark energy. And all of these lines here are supposed to say that until we understand what the dark energy is, we don't understand the fate of the universe. So for example, if it is just vacuum energy, if it is just the energy of the quantum vacuum, the universe will continue to accelerate. And in about 100 billion years, the only galaxies we will be able to see are those in the Virgo cluster. And actually in 100 billion years, we also won't be able to see the microwave background anymore, the evidence for the hot Big Bang beginning. But other things are possible. And now you're probably expecting me to tell you what the dark energy is. And the answer is, we are puzzled. We don't have any really good ideas. We have lots of ideas, but none of them. We have this term compelling. None of the ideas are compelling except to the author of the paper. And so I call dark energy not the most important problem, but the most profound problem in all of science today. Why is the universe speeding up? It's somehow related to the energy of nothing. And inflation. So I actually didn't mention inflation. So this idea, actually I did mention it earlier with Alan Guth. So there's this idea that when the universe was very, very young, it underwent a period of extraordinarily rapid expansion. Actually, it was accelerated expansion, but back in 1979 or 80, Alan and others were afraid to call it accelerated expansion because it was a crazy enough idea already. And so a small bit of the universe explodes and becomes enormous. And that makes that small bit of the universe very flat, a prediction of inflation. And we've actually measured the universe to be uncurved or flat. And the part that is perhaps most exciting, partly because I wrote a paper on it, is that the lumpiness that seeded the galaxies, according to inflation, started as quantum fluctuations on subatomic scales that by this enormous expansion got, so here they are, quantum fluctuations on subatomic scales, enormous expansion, got blown up to size that were as big as a galaxy. And so if this idea is right, the patterns you see across the microwave sky are actually quantum fluctuations on scales smaller than a billionth the size of the proton, projected in the biggest IMAX theater you can imagine, the universe. So according to inflation, the lumpiness of the universe that seeded all the galaxies and all the other structures we see arose from quantum fluctuations. Well, do you have any evidence for that? So the evidence comes from the microwave background, and this is the Planck satellite. And by comparing these temperature differences, inflation makes a very specific prediction for this. And these are the temperature differences displayed in a certain way. And here are the measurements with error bars. And the red curve is what inflation predicts. And you'll notice that the red curve goes through all the points. And so that's pretty spectacular. And so that's pretty good evidence for inflation. I'm going to skip this one. So our current paradigm for understanding the universe is called lambda CDM. So the lambda is for vacuum energy being the dark energy. DM is for dark matter. And there was a detail that that maybe Katie mentioned, is that we want dark matter particles that move slowly. The only dark matter particles that we know that move fast are neutrinos, and they aren't the dark matter, but we need slowly moving dark matter particles to get the structure we see. So we have an inflationary beginning. The seeds for structure formation come from quantum fluctuations. This sounds like some science fiction, but we have evidence for all of this. 5% of the universe is atomic matter. Only 0.5% is in stars. 25% is in these cold dark matter particles. We don't know what they are yet. And 70% is in dark energy. Okay. Oh, Hubble troubles. And I don't mean the recent pointing problems with the Hubble telescope. This is really interesting. So the Hubble constant can be measured two different ways. One way you're extremely familiar with. The Hubble constant is the rate at which the universe is expanding today. And so you can get that Hubble constant by measuring the velocity of a galaxy and its distance. And so the Hubble constant is that ratio. So it's kilometers per second per megaparsec. And it's been measured very precisely to be 73.5 plus or minus 1.5 kilometers per second per megaparsec. And this is the work of Wendy Friedman and Adam Rees and others. It can also be measured indirectly by studying the microwave background. And then you get 67.4 plus or minus a half. And these two numbers differ by 3 sigma. And this is a plot that shows the Hubble troubles getting worse with time. So this is the year published. Red is the microwave background measurements. Blue are the direct measurements. And you can see microwave background like 67, the direct measurements like 73. So you might say, whatever, one method is wrong. That could be. Actually, it could be that both methods are getting the wrong answer. But the measurement involving the microwave background assumes this model called lambda CDM, because it doesn't directly measure the expansion rate. So it has to assume this model. So another alternative is that lambda CDM is not right, that something is missing. So both of these numbers could be correct, and there's a missing ingredient. And let me jump ahead to the ending bit here, wild speculation. So I started with what we know for sure. I talked about the stuff knocking at the door. And now the wild speculation. Everybody loves the multiverse, except half the cosmology community. So let me try to quickly explain the multiverse. So this is a diagram of the Big Bang theory based upon Einstein. So it starts with the Big Bang. Here's the quark soup that you saw. Here are the galaxies today. And you can think of this as the universe getting bigger. And according to Einstein's theory, the Big Bang is the singular creation of matter, energy, space, and time. And actually, it's going to come back to my final point is, so according to Einstein, there's no before the Big Bang. That question doesn't exist because that's when time was created. But I want you to focus on this diagram and now start thinking about inflation, because this inflation event, oh, actually, now I'm going to send you to an art museum. So I want you to view this as a Monet. Blue is the cosmic river of time. And here is a little bit of the universe blowing up and inflating. Okay. And it turns out, this is an embarrassment to theorists, that if inflation happens once, it happens a lot. And when a theorist says a lot, that means an infinite number of times. So that means that this inflation is happening a lot. And so there are different inflationary bubbles. And it turns out that the universe has an infinite number of beginnings. And when I come back to what happened before the Big Bang, an infinite number of beginnings is essentially equivalent to no beginning. But each one of these bubbles is incommunicado with the others. And now let's marry this with string theory, which says that different in these different bubbles, you could have different laws of physics, like the different number of dimensions, and you get a pretty picture like that. The multiverse. Why do I have a bottle of beer here? That's to remind me to drink the beer I have in front of me. No, not really. That's because the multiverse gives us a headache, because this idea is not testable. It may be the most important idea since Copernicus, but these different regions are incommunicado, and so you can't test the idea. And the hallmark of science is you have to be able to test it. It can't just be a cool idea. We're not, science is not about cool ideas. It's about how things really are. And okay, so that's the multiverse. That's the dilemma. Here we are. You may have the most important idea since Copernicus, but it's not testable. So it's not part of the science brand. Well, but maybe we can make it testable. Okay, you get the idea. Let me end with a question that used to be, if you'd asked a cosmologist what happened before the Big Bang, they would say, oh, you can't ask that question. So that question is now within the realm of science. So here's the same picture. I'm going to just talk about what could be the answer to the before the Big Bang. What could be that Einstein, oh, I forgot to tell you, let me go back to Einstein's picture here. So I put a bunch of question marks here. So this in Einstein's theory is a singularity where the laws of physics break down, and where his theory should have incorporated quantum mechanics and didn't. And another way of saying this is where his theory is suspect. And so are we really gonna, assume that it's true? Not only isn't it testable, it's suspect because it doesn't incorporate quantum mechanics and it has a lot of infinities in it. Okay, but often in science, and often my students get the right answer for the wrong reason. So maybe the Big Bang really was the beginning of space and time, but it was the emergence of space-time, and I'll bring string theory in here again. So according to string theory, space and time may not be fundamental. You can ask me about that later. That at some point they emerged. And so space-time emerged, and Einstein got the right answer for the wrong reason. Here's another idea. String theory has all these extra dimensions. And one way to deal with them is to say that, yeah, we're living in this higher dimensional space, but we're living on a three-dimensional brane. And that the Big Bang was the collision of two three-dimensional branes. And these branes pass through one another. And when they hit, that's the Big Bang. And then they collide with another brane. And you end up with a cyclic universe. And actually, I guess I want to go backwards here. For the last idea about getting rid of, what happened before the Big Bang is the multiverse, the inflationary multiverse. Because if you have an infinite number of beginnings, you didn't really have, there is no, another way to get around before the Big Bang is there was no beginning. There were an infinity of beginnings. So I am done. Oh, I have to give the caveat here. These are three very different ideas about what happened before the Big Bang. Actually, I say they're all probably wrong. I could probably guarantee they're all wrong. The key point here is that what happened before the Big Bang is now within the realm of science. And then I just want to finish by saying, I won't go all the way back to bucket number one, but it is truly remarkable what we know about the universe. Given how big it is and how limited our instruments and our minds are. We've learned an awful lot in the last 100 years, and it's a very exciting journey, and there's a lot more to learn. Thanks so much for your attention, and I hope you have some questions.
That was great. Thank you, Doc. I was looking to see if we had some questions popping up here in the chat, and I think there's not a lot. I mean, there's
No.
I'm surprised that Bob Blasco wasn't chiming in on a few here. I was kind of anticipating that.
Oops. Let's see.
When
what
you
are-
get into what we don't know, it quickly becomes a mess.
Right. Well, I was thinking too, I mean, this doesn't have a whole lot to do with the talk, but, with black holes and dark energy and dark matter and, the next time that you come up with something, do you have to call it dark? Can you get a wordsmith or somebody that can come up with a better name than dark matter, dark energy, or a black hole, or a big bang, or Big Bang seems, at least I get that one, but
Yeah. Well,
those are,
you think we overuse the word dark?
skosh. Yeah, maybe.
Uh,
I mean, I
well,
get it that it's like it's an unknown, and that it's like it's in the we don't understand it well, and so it is in the dark side of understanding. I understand that, but
well, I know you guys are an astronomy club and you really fancy light. And it turns out that essentially everything we know about is stuff that is charged or made of charged particles so that it radiates light or absorbs light. And that I think dark means that it's not charged, it does not interact with light. And once you start thinking about it, you might say, gee, yeah, we're pretty limited. In fact, let me give you, the biologists have tried to steal our term dark. So let me come over to that. So the things that we know about are things that are made of charged particles and therefore interact with light, but there are other forces of nature. And let me give you the biology example. They're always taking advantage of us. So I'll give the biology example. So the only things that biologists knew until about 20 years ago in terms of microorganisms were things that they could put in a petri dish, throw some food in, and would grow. So they call that culturing them.
mm-hmm.
And so it turns out if that you scrape just about anything, probably my desktop here, there's all kinds of microorganisms, and most of them are not bacteria. And now we can just take the junk that I scrape off my desk and put it in a sequencer, and we find all this DNA that is not the DNA of bacteria. And so we discovered this enormous biome. And so we had a certain kind of food, and so we put it out there. In fact, it reminds me of the Viking lander. Those of you who are old enough to remember the Viking lander going to Mars, and it was searching for life, and it was going to throw out a Big Mac and see if anything came to eat it. And so I think dark is really good. It's reminding us that the only stuff that we easily know about is stuff that gives off light or absorbs light. And so that's all dark really means, is it does not, I'm trying to avoid using the word couple, but doesn't interact with light, doesn't give off light or absorb light. And that is a big, and it turns out most of the stuff, let's take the dark matter, there's 5 times as much dark matter as there is ordinary matter. And the one thing we know for sure about the dark matter is it doesn't give off light or absorb light. And so dark has a larger meaning there. I'm trying as hard as I can to defend our terms, but I don't know.
That I think that was the best I'd ever heard anybody kind of describe that. So I appreciate you putting some thought into that. My buddy Shannon is always available for any wordsmithing that you may need in the future. I would always recommend bounce something off Shannon before you ever throw anything out there. But
Okay.
he's So that's that was my question. Anybody else? Don't forget to unmute if you need.
This is Bob. There was a slide where you showed the virtual particles,
Oh, yeah.
and there was a factor of 10 to the 55th, and that's in bucket number 1. How can that be a established theory if it's not explained?
Yeah. I am so glad you asked that, because that means you're really paying attention. Let me go back to the, so what is in bucket number 1, and I didn't show you the data, is the fact that the expansion of the universe is getting faster. That's in bucket number 1. And I didn't show you the data, but here it is. We look out in space, we look back in time. So by looking out in space, we can measure the expansion rate earlier in the history of the universe. And it was less than what it is today. So the fact that the universe is accelerating, that is in bucket 1. The rest, you kind of caught me there. I should have been more careful in what I said. If we want to hold to Einstein's theory of gravity, there's a natural explanation, which is there's stuff out there that is elastic and has negative pressure. And we call it dark energy, but forget that. So we have an explanation within Einstein's theory. In fact, I had a slide here quoting Eddington. You guys will really like this. No experimental fact should be believed until confirmed by theory. And what Eddington meant is sometimes discoveries are too good to be true. And so it's slightly reassuring that the acceleration of the universe can be accommodated by Einstein's theory. That doesn't mean it is. And so you absolutely caught me. So this is one way to understand it. So probably that does not belong in bucket number 1. But the fact that the universe is speeding up belongs in bucket number 1. Did that clarify?
Okay. Yeah, that's good.
So I conflated a little bit.
Alex, I see that Moshe's got his hand up. Oh yeah, there you got him.
Oh, uh-oh.
Yeah, here comes my, you do know Moshe.
Uh-oh.
What an interesting reaction.
I'm not answering any questions about lithium, Moshe.
Hi, Mike. First of all, I must tell you, seeing your signature slides bring me joy.
I know, I love the slides too. I completely agree. They're great.
Makes me feel young again. I think first time I saw those slides was maybe 40 years ago.
Oh, now you're not supposed to say, aren't you going to be nice to me, Moshe?
Just a curiosity. So last year, we took a vote, the International Astronomical Union, to rename the Hubble law, the Hubble-Lemaitre law. How would you vote on it?
Boy, did I give some of my younger colleagues an earful. In fact, what's his name? David Merman, a very famous, no, not Merman, Jackson, who wrote the classic text on E&M, wrote a paper about this, that more often than not, things are named after not the first person, but who discovered them, but the second or third. And what he was really saying is more often than not, the namings aren't really accurate. And so it is true that a number of people during Hubble's time were kind of barking up the same tree. Lemaitre, all the redshifts were measured by Slipher. De Sitter tried to make a plot, but we we named it the Hubble law, which, and I think going back and changing things, oh my God, the list is really, really long. And if you take into account that, oh, Bode's law, you guys have all heard of Bode's law, right? And you know who discovered Bode's law? Titius. And it's just, you name it, it's named after not the first person who discovered it. And often it's even more complicated, which is what they did at the IAU, which is Lemaitre had a part in this, and Hubble had a part in this. And are we really, so what are we going to do next? And science, one of the key interesting things about science is are all the missteps and misnomers, and this is not really a diatribe against Lemaitre, but I think you're just on a fool's errand if you're going to go right every wrong and try to go back and change the name, because there are going to be close calls. And I mean, inflation is a really good example. Once inflation became an important idea, oh, you should have seen the line of people who said, oh, I had this idea earlier. But Alan Guth is the guy who stood up and said, this is really important, and wouldn't sit down. And Hubble was the guy who stood up and said, this was really important. And I'm sorry, you got a longer answer, Moshe, than I think the renaming is just, I think I finally, when I was arguing with this young colleague, I said, it's a fool's errand. I'm not saying it's wrong, but it's just a fool's errand, because you're just going to spend all your time.
We had some other questions here too. Alex, you want to take them, or you want me to just ask them up? I see that there's one from Stuart. Says, hello, it's Courtney. I was wondering what your thoughts are regarding what was before the Big Bang. How does something from nothing? How does something come from nothing? Not sure if I missed that part. Thanks. So that was.
Oh, well, before the Big Bang, I tried to say that's where we have a couple of ideas that are all probably wrong. But the key thing about those ideas before the Big Bang is they don't really answer the question. It's not like, oh, there was a guy with a firecracker. There was, oh, the Big Bang was the creation of matter, energy, space, and time. My good friend Lawrence Krauss wrote a book called Something from Nothing, or The Universe from Nothing. Yeah. And I think I think he made a lot of money on it, and I'm in the index and mentioned quite a few times, so that made me happy. But it's kind of a bait and switch. What he's saying is, if you had the laws of physics and if you had space-time, then a quantum fluctuation could create the universe from nothing. Well, yeah, where did you get the ham and eggs? It's so I think that's not, he doesn't really explain, a universe from nothing, because he started with the laws of physics and space and time. So
the certain argument.
Yeah, and that's really the big question. Why? I mean, then, I don't want to go anthropic here, but of course, if there weren't anything, we wouldn't be around to ask the question, why something from nothing? But boy, that is really the big question. And that big question, boy, I'm gonna go religious here. You could have a creator. The scientists of the Enlightenment replaced God by the initiator. Realize that you don't need a God that's running the solar system. Newton's laws will do that. But that theory is not favored any more than we are an experiment in freshman lab in a very advanced civilization. So they send out all the students, they are so smart. They can create space, time, laws of physics. And we just happen to be an experiment that went awry in the laboratory.
Well, Steve Labkoff kind of added to that a little bit too with, so before the Big Bang, was there God? He goes, it's not a wisecrack question. Is this the intersection of God and science?
That too seems circular. As soon as you say, was there a thing before there was anything, you're just setting back the question.
Right. Yeah.
Well,
The
you
chicken
know,
and the egg.
there are two questions here I want to answer. So one is St. Augustine got to this question a long time ago. He was asked, what did God do before he created heaven and earth? And St. Augustine was a very powerful philosopher. And his first answer was he created hell for anyone who asked that question. His more serious answer was Einstein's answer, which is, oh my God, it makes no sense for God just to be sitting there forever, because God is forever. And then all of a sudden, what does it mean at some point in time? So his answer, St. Augustine's answer was, God created heaven and earth when he created time. And which, you know, logically, it doesn't mean that it's true. Ugly theories are, beautiful theories are killed by ugly experimental facts. But what was the other question lurking in there?
Oh, there's quite a few that are popped up now.
Okay.
I saw
about science. So I love teaching in every course I do, spending a week about what science is all about. And I'll give you the short version. Science is the most powerful tool we've ever developed to explore the physical world, period. Plumbing is the most powerful occupation we ever developed to clear clogged drains. If you have a clogged drain, you need a plumber. If you have marital problems, a plumber is not going to help you. And likewise is that if you really want to know what the meaning of life is, a scientist is not really going to help you, because what we do is figure out how the physical world works. That's what we do. We're like a plumber. We're really, really, really good at that. But if you ask us, why is there gravity? Our answer is about as good as anyone else's answer. So scientists, I think we're just in a different business than religion.
I see that Bob Blasco's in here now. Did you have a question, Bob?
Yeah, Dr. Turner, I guess my question is about the career paths of new people coming out in astronomy. You know, there was a long time where everybody's writing Ph.D. on string theory, and, you know, most graduates were focusing on that, and all of a sudden 10 years later, I don't know if we got anything out of string theory. What would you recommend for graduates today? What's in the next 10 years? You know, I don't want to spend the next 10 years studying and then come out with nothing. What would you recommend that person focusing on? You know, dark energy, dark matter, black holes, you know, where would you focus a good career path where you think you could really contribute something?
Well, that's interesting. So I would not say that nothing has come out of string theory. I'll come back to that. And I would say that you have to do what really interests you. And you also have to be informed by what's going on. So there is just a deluge of data. Astronomy, we have built a suite of powerful instruments that are exploring the universe, and we're doing stuff that we couldn't have done 30 years ago. So anything involving data, big data, survey science, you're bound to do something good. But on the other hand, you have to pursue what is interesting to you, because most of science is not eureka moments. It's things breaking and not working, and a short defense of string theory. My biggest criticism of string theory is portfolio management. your broker put too much of your stock in string theory. It is one thing that we've learned in the history of science is progress in science has been paced by mathematics. So, you know, if you go back to Democritus and the Milesians, they didn't even have geometry. And so everything they talked about the universe was very qualitative. You get geometry. Geometry lasts, we could throw algebra in there, but geometry lasts till Newton, and then it's calculus. And so the ideas in string theory are extraordinarily powerful. And the history of, I mean, for example, at the end of the 19th century, non-Euclidean geometry, you can imagine people saying, oh my God, what a waste. I mean, what are you going to use that for? I look at the triangle on this table. It's 180 degrees. You know, we don't live in a curved space. But that non-Euclidean geometry is what made Einstein's theory of relativity possible. And so powerful mathematics historically has been required for advances in our understanding of the laws of physics. And my only criticism of string theory is there's too many people doing it. It's you know,
They're still doing it?
Oh yeah, absolutely.
Yeah, they're still writing a lot of books on it, Bob. There's yeah. Brian Greene is still talks about string theory all the time.
Yeah. And it's very exciting, and but it's you know, the worst PhD advisor in the world was Feynman. Wow. Great physicist, but he was only interested in what he was interested in. And thank God, very few PhD advisors are like Feynman. So they understand that the purpose in advising a graduate student is for them to accomplish a little piece of work and that's of interest to others so that they might get a job. And but I think right now in astronomy, just the deluge of data, whether it be exoplanets or gravity waves or black holes or yeah, there's just a lot of opportunity, and then you have to pick what interests you. What are you willing to have 6 months of completely boring backward progress before a eureka moment?
How you doing on time, Doc? You okay? I know you got a hard out, right?
Well, pretty soon I should go eat dinner, and also I should let you guys go, but I'm happy if you have a few more questions. I'll give shorter answers.
Alex,
I'm not famous for short answers.
Yeah, so one question we had is, you know, earlier in your talk, you started with billions of galaxies, billions of planets. What's your thought on intelligent life out there?
Oh, that's a really, really, really good question. And probably most of you know about the Fermi paradox. Do you all know about the Fermi paradox? Where are they? When it was explained to Fermi how many planets there were, this is before we even knew that there were exoplanets. And you all know about the Drake equation. And Fermi had several answers because what he realized is if we weren't the first civilization in this galaxy, anyone with a short head start, once they got technology, that, you know, 1 million years head start, imagine what our technology will be in 1 million years. And so there's several answers to Fermi's, you know, question. One is, well, they're sitting right next to you, Enrico. They're laughing at your question because they are here. And another answer, the sadder answer, is that something bad happens to advanced societies, or that they don't live long enough, or that something happens with their star. Another answer, which I find absolutely fascinating, is intelligence I've gone to a couple of conferences where there's evolutionary biologists, and is intelligence a convergent property of evolution? That is, if you start a bunch of evolution experiments, do you always evolve intelligence? And once you start thinking about it, you realize that's a pretty good question, that nothing in evolution is, you don't get style points in evolution. The goal of an evolution is to dominate the resources. And so it could be that the universe is teeming with life and all those planets are covered with slime molds that are, some primitive form of life that very effectively uses the resources. And that, we were this really weird experiment. If you think about it, the amount of evolution that went in before the brain was useful, just imagine all the evolutionary energy that went into evolving a brain before it was not very helpful. And, what protected us during that, whatever it is, million years where we were developing intelligence. And so it could be that the universe is teeming with life. And then there's just the simple thing that I think is absolutely fascinating. So all of you have been to science fiction movies. Why would we want to advertise where we are? The universe is filled with bad guys. We just want to, we want to put some stealthy materials over our planet and hide here. But we will find life elsewhere. I think that's the sucker's bet. And the recent finding of phosphine in Venus, it may well be like the Mars rock of 20 years ago, but it gets you thinking, why not? And so I think we're looking in so many different places we'll find life. Intelligent life, that gets really complicated because it could be that intelligent life is very rare.
I saw this other question here too, Doc, that Doc, it said from Cheng Zhao, he said, you mentioned some ideas about multiverse cannot be tested, but dark matter and dark energy cannot be tested either. So aren't they all based on calculations, and why is the latter widely accepted?
I like that question.
Yeah.
Because so dark matter is really easy. The current hypothesis is it's particles, a new form of matter. And so one way to test it is to create it in the laboratory at CERN, at the collider. So dark matter, and there are other ways of testing it. There is, Martin Rees talks about this, Jerry Oestreicher talks about this. It could well be that the dark matter is particles that we can't detect. And that gets tricky because then you could say, well, okay, it's a way of describing what's going on, but you don't really understand it. But the idea of particle dark matter is testable. Dark energy, we know the universe is accelerating, and I can't remember if it was Dan or Bob or whoever for the question. We know it's accelerating. Whether we'll ever understand the cause is a tough question. And because we don't have any good ideas, except that it's vacuum energy, but we can't calculate how much vacuum energy there is. But if we could calculate how much vacuum energy there is, there'd probably be some other test of that idea. I would also say string theory, as much as it's maligned, not being testable today is different than not being testable in principle.
Right.
And that's the problem with the multiverse. And let me defend the multiverse a little bit. So as we currently understand it, these different pieces of the multiverse don't communicate with one another. Well, that means we can't test it. But we could be wrong that there are wormholes between them, or that we just don't understand. One thing we know for sure is we don't understand the idea of the multiverse well enough to say absolutely positively it's not testable. But in its present form, it isn't testable. And so that, boy, pushes it makes it different than string theory. String theory is very hard to test. Particle dark matter is pretty easy to test. Dark energy is hard to test. But I'm not going to put particle dark energy into bucket number 1 until we actually find the particle.
All right.
Well, is this a good time for me to go to have dinner?
Yeah, I think so.
Yes,
I
it
think
is.
it is. Well, that was great. Thank you, Dr. Turner. There's other questions here and stuff, and I know
Oh,
that.
give me one more. Let's do one last question. Pick the best one.
Okay. Put me on the spot now. Let's.
Or give me 2. I'll give. This will be the lightning round. This is the Chris Wallace lightning
I'll
round.
give you, but it's probably a simple one. I
Yeah.
think referencing a formula somewhere on one slide. What does 75 kilometers per second per megaparsec mean?
Oh, that's the expansion rate of the universe.
I think the question is, what's the per megaparsec?
So that means if you want to know the apparent velocity of a galaxy, you take the Hubble constant and multiply times its distance. And the distance is measured in, you guys know what a parsec is, right?
Mm-hmm. Yeah.
And a megaparsec is 1,000,000 parsecs. So the expansion rate of the universe gives you the apparent velocity of a galaxy when you multiply times its distance. Oh, that was an easy one. Toss me another easy. We'll do the lightning round here.
And you got last question.
Me? No, I don't have any. No. I think there are some other questions here that we could certainly answer outside of this. So I think that is a wrap. And so that was really fascinating. It was really interesting. And thank you, Dr. Turner, for your time today. And hopefully we can get you to come out, and if you're out in the West or on the East Coast, come out and visit us.
Okay. Well, thank you for letting me sit in. Those were beautiful pictures, and I realize I have a lot to learn from you guys about filtering. And I went to my first eclipse. I was so lucky in Southern Illinois a few years ago, and I tried to be smart. We positioned ourselves in a car with bikes because I realized that you can outrun a cloud, and we saw that beautiful eclipse. I was not able. I couldn't get any pictures. That's where I could have used your help. But I realize I now know who to come to when I want to take pictures of the universe.
Well, don't follow me, because I took everybody to Beatrice, Nebraska, and we looked at rain clouds until the very second there, the very last second, the clouds parted a little bit, and we got the total eclipse. So it was other people in our group went to all over the country, Wyoming, and saw it.
And I bet they got pictures.
Oh yeah, we've got pictures. I mean, but yeah.
I didn't get a picture, but I said, look, I am not going to miss the experience. Next time I'll take a picture. But thank you again for inviting me, and I enjoyed this very much. And see you again.
Well, thanks for your time. Maybe we can do it again sometime in the future. So thanks.
Okay.